In this segment, we'll go into tuple types. Tuples combine data from different types in a fixed shape, and that gets called a record in other programming languages. So for example, the pair, the string hello and the value true, is of type string comma bool. So the things in that type are things with a string in the first part and a boolean in the second. There's a different type, the type you see below, where there's an example, the string hello followed by the value true followed by the string there is of a different type. It's of the type string comma bool comma string. And given any element of that type, I know the first thing and the last thing will be a string and the central element will be a bool. And in general, a tuple will have n elements, and if the elements v1, v2 up to vn are of type t1, t2 up to tn, then the tuple containing v1, v2 up to vn is of type a tuple type t1, t2 up to tn. And so tuples have that general form. They are a record, a thing of a given size, where we know precisely the type of each component in each slot, as it were. Now, how do we program with tuples? In a conventional language, what we might do is use selectors. If we were given a record or an object, we would use field selectors to pull out particular values. Haskell takes a more direct approach and says, actually, what you can do is use pattern matching to match the shape of the tuple, and so use access to components of the tuple directly, as it were. You can see an example here. I've written a function sum t for sum of a triple of integers to a single integer. And we know that any value of that type will consist of 3 fields, each of which is an integer. So we can say we know that the input will look like a tuple with elements, say, A, B, and C. So we make the input of that shape, the pattern, to match the shape we know that the input has. And so we say sum of the tuple A, B, and C, A, B, C, is A plus B plus C. So we directly say, on this kind of pattern, we know the input will be of that shape, and so we will match the variable A to the first element of any input, like 2. We'll match the variable B to the second element, 3, and we'll match the variable C to the final element, in this case 4. So A is matched by 2, B by 3, and C by 4. So in the case of taking sum t of the tuple 2, 3, 4, we will get the answer 2 plus 3 plus 4, which is 9. So these things, we use this equation to calculate, just as we've done calculations earlier on. Now we could, if we wanted, define selector functions that would first t, second t, third t, that when given a triple like this will give us a particular value, and we do that by pattern matching. So first t will take a tuple with A, and what we've done, instead of naming the second and third parts by variables, we just used a wildcard, which says, I don't care what's in this value, I'm not going to use it in my definition. So here you see first t, when applied to a tuple A, wildcard will return A. Second t, when applied to a tuple wildcard B, wildcard will return B, and so on. So we can always define selectors if you want to write that style of program. But as we saw earlier, we didn't need selectors, we just directly use the values matched to the variables that match the first and second and third parts of the input. Now, how might we use tuples to model data? An example which we will come back to is we can think of modeling a supermarket bill as a collection of of string integer pairs. Each item in the bill is a string describing the item bought, and the second item is the cost of that item in pence. So we bought a kilogram of salt for 139 pence. We bought a bag of plain crisps for 25 pence. So we're using this string integer pair to represent this piece of real world data. Now we can actually give that type a name. We can say, we're calling this type shop item. So we're saying type shop item is this type where the first item is a string, the second item is an integer. So that something like salt, 1 kilogram, followed by 139, is of type shop item. Now, this is just a type synonym. It's just another way of talking about that type. It doesn't create a new type. Items in that type are just pairs of strings and integers, and shop item is just a more memorable way of writing that type of the pair string comma int. But it does allow our programs to be a bit more readable, and it does, in a way, name our intention. In this program, we're thinking of that pair of a string and an integer as a shop item rather than something else, something like a name and an age, for example. So we have this notion of type synonym, and we will use that. It's a way of making programs more readable. It's a good way of documenting what you're doing with a tuple type to give it a name that suggests how you're going to handle that data. Now, we talked about this a bit in the introduction to the block, but just to reiterate, so a basket in this shop case study would be a collection, a list of shop items, and all the members of that list are of the same type. But the type can contain lists of all different lengths. So for example, it can be an empty basket with nothing in. It can be a basket with 1 item, a basket with 100 items. So the shop item type accommodates things of different sizes, but in each case they must all consist of, they must consist entirely of shop items. Whereas a tuple is of a fixed size, but the individual slots can be of different types. So a shop item itself we've seen is a string in the first slot and an integer in the second. Now you might ask, why is it that we can't have heterogeneous lists, like a list with the first element is the number 2, the second element is true, third element is the character \c, and the fourth element is true? Well, why is this a problem? The problem is this, that if we were to choose a random element from that list, which we could do, lists, remember, are collections, we've lumped them all together, and so if we chose the first element, we get something which was an integer. If we chose the last element, we get something that was a Boolean. So we couldn't predict, when choosing an element, what type that element would have. And that means that we wouldn't be able to do what Haskell requires, which is always knowing the type of an expression in Haskell. And so because we can, as it were, randomly access items in a list, we have to ensure that every element in that list is of the same type. So that's a requirement that's forced on us by wanting to be able to work out the type of any value, any expression in Haskell. So that's something that we have to, it's a constraint that means that lists are homogeneous, list elements are always of the same type.